Hello, my name is Roman Shupa, and it's my pleasure to present our recent results in the study of tribochemical processes through the analysis of triboemission of gases. This presentation will be focused on the application of our new methodology on advanced liquid and solid lubricants. And this work was done in collaboration with my colleagues from Autonomous University of Madrid, Spain, and from various universities from Medellin, Colombia. First of all, I would like to acknowledge the collaboration from Jaume Caro and Anton Rusanov for preparation and characterization of DLC samples and also funding obtained from various projects. This presentation will consist of four main parts. In the first part, I will briefly explain the state of the art in accessing almost inaccessible interfaces. In the second part, I will talk about gas triboemission, the fundamentals of this phenomenon. In the third part, I will discuss the Operando characterization of tribochemical processes, the recent advances in the methodology of using mass-spectrometry for characterization of tribochemical processes. And finally, I will show several case studies where this methodology was applied for studying DLC coatings, ionic liquids, and composite friction modifier. Since very beginning of the tribology studies, it was a desire of all researchers to understand what really happens in the interface. And not until the 90s of the 20th century, it was possible when the new techniques were developed, allowing to characterize the interfaces and contact surfaces in situ, on site, and even in Operando. Among these techniques, it should be mentioned the virtually in situ environment technique developed in Lyon in the laboratory of tribology and system dynamics, which includes both the tribological chamber and the characterization chamber. So the sample can be rubbed in vacuum and then transferred to the characterization chamber when it can be characterized. This is not really in situ measurement since the sample should be transferred, but this can be done without taking the sample to the atmosphere, so the tribal surfaces can be conserved without oxidation, without contact with water and oxygen from the atmosphere. However, this technique doesn't allow to measure the processes really on the site and during the experiment. Later on, various really in situ and operando techniques were developed, and this includes, for example, EXAS technique, which uses monochromatic beam of X-ray radiation to irradiate the sample surface inside in the vacuum tribometer, so it can be possible to obtain chemical information from the contact surfaces just on the site where the friction experiment was done. And the most advanced technique, including FTIR, Raman, synchrotron, XANES, electrochemical, digital holography, and other, allows measurement the processes directly on the interface during friction. But these techniques requires that one of the samples which are in contact should be transparent for the radiation which is used for a certain technique. So this technique cannot be used freely for all types of interfaces. This technique is only suitable for laboratory characterization of some certain processes which can be characterized using these transparent materials or window disk. But what about the real situation or real material combinations, which usually are metals or ceramics, which are not transparent for the selected wavelengths? So what can we do to characterize friction and wear on real interfaces which are really buried into the and very difficult to access? Unfortunately, only very limited number of techniques are available now, and I can mention here the acoustic emission and noise, which allow to obtain the information about fracture processes and deterioration, crack propagation at the interface by measuring the acoustic emission and noise. And another technique which was developed in the middle of 20th century, which involves using of radioactive materials to introduce first in the sliding interface, and then by measuring radioactivity of the lubricating oil, the degree of wear and the wear rate can be monitored in situ and in Operando. However, these techniques do not provide any chemical information on the tribochemical processes. So the probably one of the most useful solution for this situation is the use of mass spectrometry. Really, this is not the new approach, since mass spectrometry has been used for characterization of gas emission from sliding interfaces for more than 4 decades. However, many of these techniques are not fine-tuned to exploit all the potential which has this technique. So the first mention of the phenomenon of gas emission by friction probably dated back to 1961 to one of the very famous professor and researcher of vacuum science, Professor Groszkowski, who observed that when a glass ball moved inside a vacuum gauge, the pressure went up and down, and this pressure variation corresponded exactly with the motion of the ball. He supposed that this phenomenon is caused by local frictional heating at the interfaces. Later on, in 1965, and independently on Professor Groszkowski, Professor De Segovia also observed pressure variation in a glass vacuum system when a sample was manipulated, and this caused some rubbing of copper against copper or copper against glass surfaces. However, this phenomenon has not been studied in more details so far by these researchers. So after several decades of investigation by several groups, it can be concluded that the triboemission of gases includes several main sources. The first of them is emission of atoms and clusters of the material subjected to rubbing. So the material is rubbed, and the small parts of this material, particles and clusters, can be emitted by friction process. The second one is desorption of the topmost adsorbed layers. Imagine you have a layer of water adsorbed on a metal surface, and by rubbing this metal surface, a part of this water layer is desorbed, and this can be observed as gas emission. The third one is desorption of gases which are dissolved or occluded in the volume of the material. So deformation of material and also to some extent heating of material by friction can lead to emission of these gases which existed in the volume of the material. And finally, and that is the most interesting for this presentation, is that the gases can be generated during and after rubbing due to tribochemical reactions. So to measure the small gas emission caused by rubbing, you need to have an adequate experimental system, which should be principally vacuum system, but this is not the limitation. You also can do this in atmosphere, although with less sensitivity for very small gas emission. So typically the vacuum system is where you place your tribometer and where the quadrupole mass spectrometer or other type of mass spectrometer situates, and you can measure the gas emission by this device. What is very important is that the UHV system, ultra high vacuum system, should reach very low pressure, so you will have very low background, and you can distinguish the pressure increase due to friction very easily and with high accuracy. The second important part is to use dynamic gas expansion system. This will allow to quantify very accurately the emission rates of different gases. So what really you need to have is the emission chamber where the gases are emitted from the sample subjected to rubbing, and the expansion system separated by a diaphragm with a small orifice, which is typically of several millimeters in diameter, typically between 8, 10, 12 millimeters in diameter. And so the gases which are emitted from the sample are expanded from this orifice to the expansion chamber, and by the difference in pressure and knowing the conductance of this orifice, the rate of emission can be determined very accurately following these kinetic equations. Also, what is very important is to be sure that the gases which you measure comes out from the sample, from the interface between the sample and the indenter, and not from any other part of the system. So the system should be designed to avoid this parasitic gas emission from the supports, like in this system which we developed. So we have all these guides and ball bearing outside vacuum system, and they are connected through the bars from the shafts, and we have here sealing bellows which separates atmosphere from vacuum, and inside we only have one mechanical part, one sliding interface which is between the indenter and the sample. Also, it is necessary to use mass-spectrometry to distinguish between various emitted species, and also it is necessary to apply correct models to obtain the information on the to identify these species, and also to obtain the information about the chemical reactions lying behind these emission processes. Well, identifying this emission species is not really an easy task, as many researchers may think, and I would like to first mention the Morris classic study, where he used the system shown on the previous page to study tribochemical formic acid conversion on steel surface under friction. So he used the formic acid vapors introduced into the vacuum system when the rotation of the table started, the friction started, so the pressure of the formic acid decreased, and also synchronously the pressure of CO2, which is the product of this reaction, increased. And by analyzing these dynamics, by correction by the pressure of the formic acid, he showed that the corrected CO2 is the rate of CO2 production per mole of formic acid is constant. So this clearly demonstrated that the tribochemical process is constant on time and depends on the concentration of the reactants to give the reaction products as CO2 and H2. And this approach was recently applied to different systems, to different liquid and solid lubricants. However, many researchers do not pay attention to how really the identification can be done. So in many cases, in many published papers, it is easy to find such data where you can see that the mass spectrum channel with the mass to charge ratio 15 is directly assigned to CH3, but CH3 is hardly can be emitted as a gas. So this corresponds to CH3 mass ion measured by mass spectrometer. And also it should be mentioned that the mass 15 can correspond to different species. Why not ammonium? NH is a possible ion with mass 15 which can be emitted in such systems, where CN and H are present. So you should not, it is not possible to identify the emitted molecules only by mass to charge ratio. And the same situation with ethane emission, which is shown, which is easily assigned to the mass to charge ratio 26 of mass spectrometer or 28 mass spectrometer, but this also can be ion coming from methylamine or some other compounds. So this simplistic approach can lead to a significant error. And also in another study, study of the ionic liquids, also very simplistic, where the peak, very small peak at mass 34 was assigned to sulfur hydride. However, there is also isotope of sulfur with mass 34 which can appear on the mass spectrum, and the abundance of this isotope is 5%, so it is not negligible and can be measured by mass spectrometer, and this should be taken into account. And when you suggest that some of the components of the mass spectrum should be assigned to some certain ion, you should demonstrate all the possible ions coming from the same molecule. All these ions should be present. You should not say that this corresponds to CF3 if other fragments are not demonstrated, because none of these fragments can come alone from the same molecule. So to identify the emitted species, there are certain challenges in using mass spectrometry. Here you can see the three main challenges, which are highly dynamic emission, which may have bursts and transients. So by measuring the different mass to charges, ions with different masses, consequently, as usually all mass spectrometers do, you can lose the information about the dynamic process, because when you start measuring, the process has some feature, and when you end measuring, some burst can appear. So the beginning and the end of the same mass spectrum will not correspond to the same process. So it should be analyzed very carefully, and much attention should be paid to the time resolution of the processes, and to select the appropriate time parameters of mass spectrometer measurements. Also, another problem is that the composition of gases is unknown, so it is difficult to assign the ions in the spectrum to the certain molecules if you do not know the exact composition. Since many molecules can give the same ions, you need to analyze the mass spectrum as a whole, and not just selecting one channel and assigning this channel to certain molecule. And another serious problem is that when you subject the material to rubbing, you can produce also radicals, and radicals can modify the mass spectrum, so it should be analyzed very carefully to be sure that the spectrum of some molecule include all the components in correct proportion, and that there is no contribution from radicals. And if you see this contribution, so it can give you very valuable information which cannot be obtained by other techniques, and this information can be obtained in situ and operando. So what our advancement in this field were to develop new approaches which consist in development of the procedure for correlation and statistical analysis of mass spectrometry signals of all ionized fragments, is aggregation of mass spectrometry by the type of time series behavior. So we analyze not only the peaks on the mass spectrum, but also we analyze the behavior of time series. So, and we can distinguish, which can help us to distinguish to which molecule correspond each ionic component. And finally, we can also analyze the time constant of transient processes, which provides very valuable information and accurate quantification. Well, if we need to analyze what are the composition of the emitted gases, so we need to analyze the mass spectrum and compare this mass spectrum with standard relative abundances of ions, or standard mass spectrum which can be obtained, for example, from NIST or some other databases. Here you can see on the left, you can see the standard mass spectrum for different gases such as hydrogen, methane, ethane, CO, argon, and so on and so on. And you can see here the relative abundances, which, for example, for CH4, the main peak is mass 16, and then the peak at mass 15 should be about 89% of the height of the peak 16, and so on. So if you have the mixture of these gases, you will have the superposition of different mass spectrum multiplied by certain coefficient, which is proportional to the concentration of each gases in the mixture. Well, first of all, how we can use this mass spectra for analyzing if there is some emission of radicals in the presence of radicals in the main gas. For example, in this case, this is a study of emission of gases from hydrogenated amorphous carbon, where the peak of methane was quite intensive. But also it is not discarded, since the mechanism of emission is bond breaking between C and methyl group. So this methyl radical can also escape, and theoretically it can be found in the emission gases. So how can we probe the presence of these radicals in the emitted gases? First of all, we need to find the correlationships between the different channels of mass spectra corresponding to methane. So we need to find experimentally this. We need to make this plot of different channels from 12 to 15 respective of channel 16, and this give us this linear fits give us directly the slope of these fits gives us directly the relationships between the masses selected in relationship with mass 16. So in this case, we had 4 different samples with different hydrogen concentration, with different technology of deposition, and we measured these relationships between the intensity of different signals, and we compared it with the abundances of the ions corresponding to the pure methane. And what it was found that in all cases these relationships were equal or smaller than the theoretical ones. So this means that there are no evidences of methyl radical triboemission. This is quite clear from the chemical point of view, since methyl radical is very active, and when it finds some neighbor molecule, it can abstract hydrogen, and so it will complete its configuration and will form methane molecule. This is why we only can observe methane in the spectrum of the emitted gases when rubbing carbon coatings. Quite similar results were obtained in analyzing the mass spectra of various ionic liquids. And here you can see the comparison between the theoretical mass spectrum of methane, which is the gray bar, and the corresponding spectrum obtained during triboemission from this ionic liquid with this cation, with this dicationic ionic liquid with imidazolium type, and with butyl side chains and ethylene glycol connection chain. And so you can see here that the relationship between mass 15 is very clear, is very close to the theoretical one. However, in masses 12 and 14, there is a certain excess of ions in comparison with theoretical mass spectrum. What does it mean? This means that if we have only methane, if we had only methane, this relationship would be very similar to standard mass spectrum. But the excess of these ions means there is some contribution from different molecule, and this molecule can be butyl. This also comes from the comparison of the channels 42 and 43, which correspond to these propyl various propyl ions, and experimentally we found that the ratio of 42 to 43 was 0.48 when the theoretical value should be 0.12. This means that there is excess of these ions in comparison with the mass spectrum of butane, which can indicate that there is also some emission of butyl radical, and this butyl radical, which has two methylene groups, can contribute to masses 12 and 14, which is the mass of the methylene group, not the methyl group. And similar results also were obtained, well, not similar, but this similar analysis was applied to the analysis of the CF and CHF emission. What we did is we plotted two mass spectrum for CF4 and CHF3, correspondingly the gray and the black bars, and the experimental results from the triboemission of the same ionic liquid. And you can see here that the experimental data do not correspond exactly to any of these compounds, but there is closer correspondence to CHF3, for example, in this case with the mass 51, which means that in contrast to the general belief that there is emission of CF3 and formation of CF4, the there is a bond breaking between carbon and sulfur, and this CF free radical then abstracts hydrogen from environment, from somewhere, and then forms CH3, which is then ionized in the spectrometer, and then gives us this spectrum which we can analyze. So our conclusion was that it is definitely there is definitely presence of CH3 rather than CF4. CF4 probably can exist, but the dominating concentration is of CH3. So these possible reactions were explained like the first adsorption of anion on the hydroxided zirconium oxide, and then this HF, and then this adsorbed anion under mechanical action can lose this CF3 group, which can react with HF or with some other compounds and produce CF4 or CHF3. In many cases, the mass spectrum of triboemitted gases is so complex that it is very difficult to analyze it. This is especially the case for polyethylene glycol compounds, which produce a number of different products with very similar ionization mass spectra. So the same ion can belong to more than one different compounds, and this makes the analysis very difficult. So we suggested the next approach to help us to separate the ions, identify these ions, and assign them to different emitted molecules. And this method consists in analysis of time series. So if we see the time series of different mass spectrometric channels, we can see that the behavior is quite different. So if we group the channels by behavior, we can see that they definitely show us that they can correspond to certain molecules. So how this can be analyzed? First, the behavior mode should be identified, which here are called denoted by different Greek letters. Then the different groups should be made up according to the same behavior, and then it is very important to analyze these rising and falling edges, and what information can be drawn from this analysis. Well, the first, you can see that in this case these two channels correspond to CF3 and CF4 and CHF3. So you can see that there is a very steep rise at the beginning and very steep fall of the signal just when the rubbing stops. So this means that there is instantaneous emission with mechanical action. In case of alkyl emission, which correspond to mass spectrometer channels 14 and 15, you can see also very abrupt increase of the signal just at the beginning of sliding, but then the decrease is not so steep. So this indicates that we change the system. I mean, the system means the surface and the ionic liquid, and then these changes still produce the emission, and this emission can be due to desorption, can be due to diffusion, or due to relaxation of some active species which contribute to the generation of these gases. And the most interesting case is of this type alpha, which corresponds to sulfur oxides, and you can see it is very slow increase, it's very slow kinetics, and all the same very slow kinetics at the end of rubbing. This is a clear indication that the process of COX emission is not directly related with rubbing. It's not bond breaking by rubbing like in the case of CF emission, but in this case we have clearly secondary process or process which occurs in more than one step. The first step can be bond breaking, alteration, some kind of alteration of surface, generation of active sites, and then the secondary reaction takes place, and this secondary reaction gives rise to emission of sulfur oxide. To distinguish between these instantaneous and retarded reactions, it is very important to analyze the leap at the end of rubbing. You can see in this graph, for example, this leap is approximately half of intensity. This means that the instantaneous contribution of instantaneous process is approximately half of the total emission, and another half is retarded emission, which can be related to the secondary processes. In the case of CF-free emission, almost all emission comes from the instantaneous process. So as a conclusion for this page, we can say that there are different tribochemical processes which can be instantaneous, like bond rupture, which is characterized by the leap at the end of rubbing, and also it can be generation of active species or sites and secondary reactions, diffusion, desorption, which lie behind retarded emission. Then when we from these analyses, when we identified approximately the composition of the possible molecules which can be emitted, then we should apply this mathematical model to a statistical model to determine the concentration of each of these components using these matrix equations. In this case, the A is the standard mass spectrum obtained from NIST, and P is the measured mass spectrum. So by applying this equation, you can get the concentration of the components which you model. So the first, you need to make the model. You need to suppose the composition of the emitted gases, and then you apply this mathematics, and you get the relative concentration of these components. But maybe you are wrong in your model, so you need to check, you need to make up different models, and need to apply this mathematics various times, and to check the quality of the fitting, the quality of this data. And for example, here this data correspond to the mass spectra of gases emitted from carbon samples, and you can see that the best fit was obtained for this model, including 6 components. And if you withdraw several components, you can the fit is not so good, and if only 2 of the gases are used, so the quality of fit decreases. So you need to select the model which gives you the best result using the step forward and backward elimination procedure. Then you finally decide, you selected which model is the most adequate to your situation. You can quantify and determine the emission rate using the time series and the parameters, time series of mass spectrometric channels, and the parameters of the system, such as the volume and the conductance of the diaphragm or orifice. And then you obtain final results, which are desorption rates, which can be expressed in SI units or in moles per second, for example. And here you have the results for four samples from D1 to D4 carbon coatings, and you can see here these results in moles per cubic centimeter and in SI units. And now I would like to show you how this methodology was used in studying of carbon coatings, ionic liquids, and friction modifiers. So, as I told you before, we characterized triboemission from 4 coatings. All of them are amorphous carbon coatings with quite high hydrogen content, between approximately 15 and 44%. And these coatings were obtained by IBD and PCVD processes with using different precursors and using argon gas in some cases. And here you can see the triboemission spectra obtained for each coating. You can see there is clear correlation between the concentration of hydrogen in the coating and the intensity of hydrogen and methane signals in the mass spectrum. With increasing the hydrogen concentration in the coating, we see dramatic increase in the hydrogen peak and also increase in the CH4 intensity. It was concluded that the generation of these gases should be by bond breaking due to shearing, and recombination of the radicals with hydrogen or CH molecules, which give rise to emission of methane and hydrogen. What is interesting also is that the behavior of methane, the relationship between methane and the hydrogen emission is not linear. So the more hydrogen we have in the coating, the higher is the ratio hydrogen to methane. Here you can see this cross-correlation graph for methane versus hydrogen for the D3 and D4 coating. This is the maximum hydrogen concentration. This is the second hydrogen concentration. So you can see at the beginning the ratio is close to 1 mole of methane to 1 mole of hydrogen, but during friction it decreases and we have 10 times more methane than hydrogen. In case of highly hydrogenated coating, it is more stable with friction duration, and it can be found between 0.4 and 3 ratio. This means that there is much higher relative concentration of hydrogen than methane in this case. And this corresponds well with FTIR analysis of the samples, which shows us that in the case of this D4 sample, these spectra, we have high concentration of methyl group and also of chain methylene group. This means that we have more polymeric structure of the coating than in case of D3, where we have higher contribution from sp2 carbon. So the larger number of CH3 groups we have, the higher intensity of methane, and so the high probability that two hydrogen form the molecule, and this molecule will escape from the substrate. Also, it was interesting that only in the case of highly hydrogenated carbon coating, we also found a small contribution from ethane and propane. And this can be explained by the reaction between neighboring CH3 groups. So we need very high concentration of terminate methyl group at the surface, so that by shearing we can break the bonds and this methyl group, methyl radical can recombine not with only hydrogen but also with CH3 group and to form ethane and probably also the propane. In case of ionic liquid, the analysis of the mass spectrometric data is much more complex since we have much more components in the mass spectrum. So in this case we applied this Pearson correlation model, and we developed this table which shows you the correlation coefficient of correlation between different masses. And from the analysis, from the careful analysis of this data, you can find some compounds which are not which cannot be supposed only from the chemistry of the ionic liquids. For example, these two strong correlation signals, two strong correlation between the mass 30 and 15 and 16 can indicate probably that there is some methylamine emission. And methylamine emission is quite strange since we have nitrogen in imidazolium and also we have nitrogen in the anion group, and it is known that imidazolium is hardly can be opened. The ring of imidazolium hardly can be opened by friction. So it is probably there is some reaction between this nitrogen coming from the anion with some alkyl or radical coming from the side chains of the cation. And these types of reactions have not been reported so far, and this is very interesting to observe that there is probably some chemical reactivity between the products of cation and anion tribochemical decomposition. So the process of degradation is very complex, and it's mainly decomposition and depolymerization of polyethylene glycolic chain and detachment of the side butyl chain, which can be observed as this part is the emission of butyl, the mass spectrum of the butyl part and the glycolic part. But the detailed analysis of other data can shed light on possible other types of reaction which have not been studied carefully so far. What I told you before, what we found from the analysis of this spectra is that there are probably also emission between sulfonic group and other products of reactions decomposition like CHF3 and probably this methyl radicals, so which give rise to the formation of these probable compounds. We do not know exactly which compound is, but the mass spectrum of these three compounds have some components which cannot be explained by other one. So we found in the mass spectrum some components in the range of 50 and 60 which cannot be attributed to any other compound of the ionic liquid, but it can indicate, it can point at the formation of these compounds which are products of the reactions of the products of decomposition of anionic and cationic groups. And finally, a very interesting result which was obtained recently is concerned the tribochemical reaction in solid lubricant, which is a composite of molybdenum disulfide and carbon nanotubes in vinyl ester matrix. This is a friction composite friction modifier which is used for lubrication and controlling friction in the contact between the rail and the wheel in railways. And what we found is, here you can see in this graph is the comparison of the only vinyl ester matrix, the blue bars, and the fully and the full composite, including both additives. So you can see here the strong increase in the emission of sulfuric compounds such as sulfur, sulfur hydride, sulfur oxide. Probably here we have this composition with methyl, and also very interesting is the emission of CS2 and COS. Why is it interesting? The matter is that under heating of carbon with sulfur or sulfur composite, these two compounds have not been observed at any temperature under heating and thermal pyrolysis in vacuum or in atmosphere. So this means that under friction there are different types of chemical reactions which lead to formation of the bonds between carbon and sulfur. And this probably comes from the carbon probably comes from the carbon nanotubes, since we have here that after friction the carbon nanotube, this displacement of the shift of the peak indicates increase of disorder and increase of the number of edges. And the Raman spectrometry also shows that the carbon is closely related, its position is closely related to the position of molybdenum sulfide crystals. So it is clearly a reaction between carbon and molybdenum sulfide which lead to formation of these CS compounds. The question now is, can we find some CS solid compounds on the surface? So we are still working on this topic, and it's very interesting for us to know, is there any influence, is there any chemical modification of the surface by the combination of carbon and sulfur, and maybe this is another and probably this is a different tribochemical mechanism of the well-known improvement of tribological properties by the combination of carbon and sulfur. And finally I come to the conclusions. First, triboemission of gases has been proved being a powerful tool to probe tribochemical process in situ and in operando. So you can obtain information during the experiment, or even in the real system if you have some measuring devices to measure the emission of gases. The gas triboemission allows identification of emitted molecular and radical species. This is very important and very different from other conventional techniques. Also, we can determine the underlying tribochemical processes by analyzing the time series and time constants of retarded emission. So we can identify which molecules proceeds from the bond rupture, from radical reaction, adsorption, etc. And finally, the reaction rates can be accurately quantified, so we can obtain also quantified information. Thank you very much for your attention.